Hi, everyone. Welcome and thank you for joining our Synergy webinar series, where we design the next hour to share case studies using complementary techniques that examines one application from different angles. My name is Julie Chen Nguyen, and I'll be monitoring those in the background. We'll have a Q&A session at the end. Okay, so it is my great pleasure to introduce you our speakers today, Dr. Katie Bell, Director of Water Strategy at Brown & Caldwell, and Dr. Martha Wells, Chemical Consultant to Brown & Caldwell. Dr. Bell has over 25 years of professional and research experience in water and an extensive experience with regulatory guidance. She has served in the development of U.S. EPA guidelines for water reuse. Dr. Wells comes to us with a wealth of government and academia and industry experience. She's a guru, if you will, in the water treatment sector. She's definitely a sage who needs no introduction. So I think that's it from my part. Katie, I'm ready to pass the ball to you. Would you please, or Martha, would you please share the screen, and then Katie will be presenting.
Well, thank you so much for joining us today for this joint webinar. I really want to express my thanks to Julie for hosting us. It's an honor to get to present with Dr. Martha Wells today. We have a long history of collaboration together, and I should not mention it, but I will, to talk about how long we've been working together. But she was an advisor for one of my master's degrees early on, and we've been collaborating ever since. So this presentation sort of culminates a large range of case studies that we've been working on in the water and wastewater industry over the last number of years. So we do want to take the opportunity to also make a shameless plug, Julie, about what Brown & Caldwell does in the water research and treatability arena. And then I'll be handing it over to Martha as we talk about how we take some of the fundamental characterization information that we develop using HORIBA instrumentation, and we operationalize that so that we can put it into practice. So we really leverage these tools to help our clients along the way. And some of the tools that we are talking about using today are the HORIBA Aqualog, dynamic light scattering, laser diffraction, and zeta-potential. So we'll go ahead and hop on to the next slide, and I'll give our shameless plug about Brown & Caldwell. We are one of the few 100% environmental, 100% employee-owned firms left in the industry with the purpose and passion of safeguarding water and maintaining infrastructure and restoring our habitats to keep our communities thriving. We actually were started in 1947, and we really stand on the shoulders of giants in terms of their vision for leveraging innovation and research in our water and wastewater treatment world. So I did want to take a minute too, that we have a stage gate process that we use in advancing both innovation and research into practice. And what we see is that the integration of fundamental research through partnerships is critically important for us to be able to advance early technologies and approaches with our client partners. We do have a treatability testing laboratory located in Nashville, Tennessee, and that's where we have built up and house our equipment systems with a heavy focus on characterization of organic matter. If we start to dig into water and wastewater treatment, it's all about organic matter. But these tools enable us to really be able to characterize and differentiate the behavior, fate, and transport origins of organic matter in a way that allows us to optimize treatment performance. All right, Martha, I think this is you.
Okay. Well, hello, everyone, and thank you, Katie, and thank you, Julie, for inviting me to talk to you today. And I have a We have prepared a slide deck that is packed with information, and it is my understanding that after this, the slides will be posted. So I may move quickly through something. You may have questions, or you may want to check out the slides at a later date. But when we're talking about aqueous organic carbon, even as soon as 15, 20 years ago, about all the tools we had were UVA 254, TOC, DOC, COD, and these surrogate measures are fine, but they don't give us a lot of information about the character transformed at each treatment stage. Organic carbon presence decreases effectiveness of oxidants and disinfectants, and virtually all water treatment processes are affected by dissolved organic matter. And so water treatment and wastewater treatment uses a series of treatment trains to remove organic carbon, but no one particular method is adequate for carbon removal in water treatment. And so I'm going to be mostly talking about non-living organic carbon in water, and we can talk later about how we limit that. So I'm not concentrating on like bacteria and so forth in the water. The segments that I am interested in and using the HORIBA instruments for come in mostly biogenic and diagenetic. Anthropogenic compounds such as we think of pollutants and pesticides and pharmaceuticals and so forth, they are present in the water. We're not particularly analyzing for those with these methods, but we do note the biogenic proteins and so forth, and the diagenetic, which is the newest term for fulvic and humic acids. It's probably the fulvic and humic acids may be the most mysterious to some of you and to me as well. After working and learning about them for decades, there's much more to learn. Term humus was coined in 1761, and soil chemists have been working on learning about humic materials for about 2.5 centuries. And those of us in aquatic chemistry, we're newcomers to that field. We've only been studying this about 100 years. So the current thinking is, are we talking about molecular, macromolecular, or supramolecular chemicals? And in my opinion, and I'm going to be giving you my opinions today, the answer to all of this is yes. Certainly the anthropogenic pesticides and so forth are in molecular states. The proteins in water are macromolecules, and supramolecular, if you're not familiar with this term, it is the chemistry of the intermolecular bond. And so we're going to find that in organic matter and water, it's very important, all of the interactions and the aggregation and dissipation that goes on in our water. And I call the organic matter and water soft matter as opposed to condensed matter. And when we get to talking about particles in dynamic light scattering, condensed systems would be like polystyrene beads or gold nanoparticles and so forth. The soft matter is this organic carbon and water that can aggregate and disaggregate. Now this slide may seem a bit self-serving. This is some of my history, research history in humic studies, but I have a purpose for adding this and remembering to tell you that every time there's a red bar here on the slide, I've had an epiphany moment, and I want to tie that back to improvements in analytical measurements and in analytical equipment has helped us as we go forward to learn more and more about organic matter in water. And that's why I'm very excited about the HORIBA instruments, because we use a suite of their instruments, and each of these instruments is adding to our understanding and knowledge. So in the BC Treatability Laboratory in Nashville, we do a suite of characterization methods. We still measure TOC and DOC. We do the HORIBA Aqualog, the HORIBA SZ100 for zeta-potential and dynamic light scattering. We have the HORIBA LA960 for laser scattering for particle size distributions. Just as a rule of thumb, we always measure pH and conductivity on every sample, and I advise you to do that. And then we also do size exclusion chromatography. And we use the information from the HORIBA Aqualog, the fluorescence wavelengths, in the fluorescent detector in size exclusion chromatography. So it is truly a suite and integrated amalgam of information. I just quickly want to go through their things to remember about sample containers. I'm very particular. Again, these slides, you can read all this at your leisure if you are further interested. We use virgin, amber. These are light sensitive materials after all, and they are certified contaminant-free sample containers. We use Teflon lined caps, and that would be for all of that suite of analysis we're talking about. Sometimes glass and Teflon is absolutely not what you would use. If you're analyzing for PFAS, then you can't use either one. But for these containers, we do use these EPA certified containers. If your container is contaminated, you lose out on all the rest of the analysis. We do in blanks. You may think it's overkill, but it really isn't. We use liquid chromatography, mass spectrometry grade water in field blanks and trip blanks. And here again, this is the voice of experience telling you. On one study, we had a sampler go down to the grocery store and pick up distilled water at the grocery store, and it had a great deal of fluorescence background in it. So that's a waste of time. Hold times should be filtered within 48 hours for DOC, dissolved organic carbon, and analyzed within 7 days, or as soon as possible. TOC analyses require different measurements. And so there really is little sample preparation as far as analytical methods go. We do filter these samples. That gives us DOC. DOC is just a operational definition of what passes through a 0.45 micrometer filter. And we use polyether sulfone membranes. You want to be very careful about the filter that you use. If you should have to dilute a sample, and we haven't had to in the HORIBA instrument, we can adjust conditions so that we don't usually have to dilute. But again, if you dilute, use LC-MS grade water. Scrupulously clean quartz cuvettes. And in the Aqualog manual, and their manuals are great. And we've had our technical staff brag on your Aqualog manuals, Julie. They like them. There's a method there for using nitric acid and detergent to clean quartz cuvettes. In the past, I've also used aqua regia. And so these are Stringent cleaning procedures, cuvettes are expensive, but you will need to have several on hand because the aqualog goes so fast, you'll take a longer time cleaning cuvettes than you will in processing samples. Okay, and if you want to be sure you have non-living organic matter, we do, especially for the DLS samples, we add sodium azide, and it's a biocide. It is a hazardous waste, and then your sample becomes a hazardous waste. So, but we haven't added sodium azide to EEM samples. Again, this filtering, you may choose to do it or not. You may choose to run samples with or without, and that's entirely up to you. So the phenomena we're talking about today is fluorescence and scattering, also UV absorbance and scattering. I know most of my career I've just called it UV absorbance, but UV visible is actually extinction, UV visible extinction spectroscopy, because it does, because you have both absorbance and scattering. So the aqualog, as I'm going to mention, it's two instruments in one. You get the fluorescence and the UV absorbance. You know, prior to the aqualog, I had to use a spectrofluorometer for the fluorescence and a spectrometer for UV visible, and measure them separately. And you have to measure both to do EAMS properly. Okay, and we'll also talk about scattering, the DLS by the SZ100, the LA960 for larger particle sizes, and as a smattering of electrophoretic mobility thrown in terms of zeta-potential. So again, quickly, this is, again, you get two instruments in one in the aqualog. And although I'm not a salesperson, I don't get a kickback from HORIBA, but we love this equipment, and I can tell you that honestly. And again, one reason I love it because it's one instrument, and previously you had to purchase two. Then it also, the aqualog, you can use it to do PARAFAC, parallel factor analysis, and another thing here, let's see, let me go back. Okay, what I want to show you is from HORIBA, we also purchased a couple of the remote software licenses. We did this even before COVID, but now it allows us to not tie up the instrument when we're looking at information. It allows me to look at it remotely from the lab. Okay, here's some screenshots from the aqualog, and also we can point out these are EAM spectra, excitation, matrix, fluorescence spectroscopy. And you may see in the literature, you may see the EX excitation on the x-axis, or the EM emission on the y-axis. In the inset, you see the spectrum has been flipped 180 degrees and then flipped 90 degrees. And in this one, you have the EM on the x-axis and the EX on the y-axis, which is the mode in which I personally like to see them. But you will see both in the literature. Okay, in this spectrum, this is I've got a couple of slides that I've used for training, and this particular one is not from the aqualog, just pointing it out. But the reason I have included this is because I want you to see this is the spectrum, the Raman spectrum of water. Now, the Raman spectrum of water is a blessing and a curse. Well, it's a curse because it interferes with the fluorescence, and so we have to get rid of it. And you get rid of it by, we run a background water spectrum. HORIBA supplies a sealed, very, very pure water sample. That sample is run with every batch, and then it is subtracted from every spectrum, and that's how you get rid of the scattering, the water Raman spectrum. The reason it's a blessing is because we can use the Raman spectra it's innate in water samples. It's from scattering by water molecules. And so it gives us a point to normalize against. And so we use the Raman spectrum for normalization. Okay, here's some other older slides I had, but this is what I want you to point out. First order Rayleigh scattering and second order Rayleigh scattering. The sky is blue from Rayleigh scattering, and first and second order, it's akin to a, if you've ever seen a double rainbow, you're looking at scattering phenomena. Okay, now this slide is not to scale, and I'm going to talk about something we have to get rid of in EM spectra, and this is primary and secondary interfiltering effects, IFEs. And if you notice, I've given you a reference here, and if I could find a more up-to-date reference that does as good a job as this one, as explaining about interfiltering effects, I would have added it here. But this is a very good reference. And so what happens, again, this is not to scale. The interrogation zone is really larger in a cuvette. You don't want your light, you don't gather the data close to the inner walls of the quartz cell. And so you have excitation energy coming in, and you're measuring emission going out. Fluorescence is always measured at 90 degrees. The EX on this end would be UV absorbance or visible. But the deal is that between the wall and wherever that interrogation zone is, and then into the interrogation zone, molecules, especially the diagenetic, humic, and fulvic, they will absorb some of your excitation light before it ever reaches all the sample. I liken them to a black hole. They love to absorb light. And so there would be an attenuation of your signal because of the interfilter effect. And then on the way out, there's also attenuation of the emission signal. So we have to correct for this. And I can't tell you how many hours it used to take me to do this back in the beginning, before the aqualog, when it happens near instantaneously to correct for these factors. So all that scattering, the Raman, the Rayleigh, the interfilter effects is really a quenching effect. We want to get rid of all of that. We want to just get down to the fluorescence. And here I'm showing a menu from the HORIBA Aqualog manual. And you can see that it is very much simplified. You can interpolate your data. Here's the, correcting for interfilter effects is as easy as clicking a button, and Rayleigh, masking, etc. And so we're trying to correct for all of this. And I mentioned the Raman normalization. Let's see, that's over here, the Raman and normalizing that. You're using that innate Raman spectrum of water to correct for two main things, I believe. You're normalizing for temperature. Fluorescence is very sensitive to temperature, especially in the South. Our temperature is not always the same day to day, but the Raman normalization will normalize for temperature, and it also normalizes for lamp life, because if you measure a data set today and 2 months from now you measure another data set, your lamp will be older. Okay, so let's look. This is a this is an EM spectrum, and I specifically like to point out that this is a spectral separation. And this just amazes me that we can get tyrosine, tryptophan SMP-like soluble microbial products like fulvic and humic-like, just by spectrally separating. Now here is something that we have noticed in doing our EAM spectra. This is from our HORIBA Aqualog. Something that we ran into, that, you know, we're usually doing just data sets to understand the entire data set, but we have found that the Aqualog is so sensitive that we can find when we have potential sample contamination. This is a 3D spectrum. It was contaminated with tryptophan in some way, probably maybe a biofilm type of contamination. And so we can do the spectrum, we can do a profile plot, and we can do a 2D excitation spectrum. The 2D excitation spectrum would be like going here at 225 and doing a two-dimensional spectrum. Profile plots are different. They put all of the information in that spectrum into it's two-dimensional, but it's called a profile plot, and you can read more about that at NIST. Now here's some scribbling. They can see this is my scribbling, and this equation, this is the PARAFAC equation up at the top, where it's really just algebra. If you want more information, here is this information. You get out three main types of data sets. You get an A, a B, and a C, I'll describe. And this is just an error term, but this is the PARAFAC equation. It's not calculus, it's just algebra. I'm not going to go through this. This is something I put together to explain more about the PARAFAC model. You get these three, A, B, and C, sample scores, emission loadings, and excitation loadings out of the data. And here again is a summary of that. Scores is A, and these come directly out of that PARAFAC equation, the different types of loadings and scores information. I export these to Excel, and then you can graph them using anything you want. Okay, so you have your EAM with the Aqualog, and what do you do to perform PARAFAC? Well, this is the symbol in the Aqualog that you click on to initiate the PARAFAC modeling, and I give you this word of advice. This again, all of this is my opinion, but I randomize the data before I do PARAFAC, and I don't know if anybody else in the world does that, but I do, and especially because we're working with treatment trains or RSSCTs, rapid small scale column tests, in which the organic carbon may go up from treatment to treatment, or it may go down through a wastewater or drinking water treatment. And I find that you need to randomize that, because you get down here to the end and you validate your data, and split half analysis doesn't work well when you have a sample that's unrandomized. So yes, it's a pain. And you have to randomize the data. After you get done, you have to unrandomize the data. But if you do that, you'll thank me later. And here's another thing you'll thank me for: keep up with the identity stamps on all the models you create. If you ever do this, you'll know what I'm talking about. And so when we do this, we get, and here's a reference that and again, we'll get to the references, and you can contact me and I will send you any of these references you're interested in. The where we have different components. Here's a 2D and a 3D out of the PARAFAC. It tells you the different types of components that are present in your water. And here's another one. And this is one that's been done on the HORIBA Aqualog in the lab at Nashville. And I picked one of the lowest DOC samples that we have done. And you'd say, well, why would you see this purple graph? Why would you put in information there with that noise? But that's because I want to show you that it's very sensitive. And we have, for this sample, it was below detection limit in DOC. So essentially, it was totally a black box. You had no information without the performing EAM PARAFAC. And so this particular sample, the primary component is soluble microbial product-like materials, 80%. Fulvic humic-like here is only about 11%. And in this model, it did not separate out fulvic and humic. Sometimes it does, sometimes it doesn't. And then we have tryptophan, which is the green in the plot, and just 2% of the tyrosine-like proteins. And they are here, and you can't compare these magnitudes. The magnitudes you need to compare are up here. This model explained 94% of the variation in this data, and these add up to 100% of the 94%. How do I know to make these assignments? Well, from years of doing it and reading about it, these are my assignments. You will find in the literature and talking to other people, they may assign them differently. And you know, we can discuss that if you like, but this is how I assign them. Okay, let's spend some time talking about particle size distribution. And in this HORIBA, in the HORIBA systems, the two that we have in the laboratory at Nashville is laser diffraction, LA960, or the dynamic light scattering, the SZ100. And you see we are targeting different size ranges with these two instruments. Okay, so let's talk about DLS. Now, DLS measures Brownian motion, and then Brownian motion is put into the Stokes-Einstein equation to convert it to a particle size. There are in the instrumentation, there are 3 different types of modes. You can look at intensity, volume, and number. I suggest if you're just starting out and learning that you check out all 3. And the DLS can be used, like I said, for condensed material, for hard material, your polystyrene latex standards. But soft materials are those which are deformed by thermal or mechanical stress, and the organic carbon in water is that kind of material. And so we have an elephant here, and we'll talk about our elephant again in a minute. But remember, this measures the hydrodynamic volume, and we've shown our elephant in an extended conformation here, and it shows a lot of space. But there, it is assumed, you know, in using the Stokes-Einstein equation, every particle is assumed to be a sphere. And I just always like to point out that it's not always a sphere that we're measuring, but that is how the theory works. Okay, here is one. I'll show you another PSD. This is from the SZ100. Again, you can do 3 modes. You can do 2 different scattering angles. I personally prefer the 173 scattering angle because the scattering angle at 90 might not be preferred for things that fluoresce. And the organic matter in water does fluoresce naturally. So again, you should try on different samples. You should try both angles. In this instance, we found a particle size of 186 nanometers. It does have a range here. And for the soft matter, the upper detection limit is probably closer to about 3 micrometers. And for the harder matter, it's closer to 8. But let me tell you what you can see sometimes in this supramolecular soft matter. And we've seen this with different instruments, with different samples. Okay, these are 3 DLS spectra coming down the page. This was at time 0, and we're getting about 0.4 of a nanometer. If you let that sample sit for 2 minutes, Then we get about 705 nanometers, and there is a hint in the Z-average measurement that there are larger particles are forming. And here again at 5 minutes, it's a little different, but it's kind of settled down. So you may want to, in your work, do time measurements. And I'll tell you a little bit why about that. Okay, now our supramolecular elephant. I think of dynamic light scattering for organic matter as being dynamic light scattering. One dynamic is for Brownian motion that's measured, but it's also the other dynamic is for the disaggregation, aggregation that is constantly going on in these huge supramolecules. So if you recall, I'm showing you I'm telling you that we see in that Z average some the hint of a very large particle, large in volume, but few in number, as few as even 1, but it's 10 times, 5 micrometers is 10 times the filter size. So you see, and of course, this is an issue in filtration in water treatment. Once supramolecular NOM is passed through a filter, it can reaggregate on the other side, and that's always a problem. And so you also have to think yourself, how does something greater than 1 micrometer float? And that would be an issue for another day. I am giving a webinar at this fall's ACS meeting on supramolecular organic matter, in case you live through this one and want to listen to me again. And so our third partner, I say a third partner, she isn't speaking today, but Katie and I have long worked with Dr. Holly Stretz, who is the interim chair of chemical engineering at Tennessee Tech University. And she and I have several publications, and this is one in which we have shown this formation of, they exist as metachemical hydrogels, and with quiescence, they can form a physical hydrogel scaffold. So this is our most recent conceptualization of organic matter in water. So I'll skip this, you can read it. So let's talk about the LA960 just a bit. So this one is using laser distribution, and here we are doing much larger particle sizes, as you can see in the diameter here. I believe that this result, a median size of 4.4 micrometers, it has to do with a study of a coagulant, and so that is what this is being used for in our laboratory, to look at larger particles. Okay, another example is one in which these larger particles are considered in wastewater to determine whether UV disinfection would be a good fit for a system. And then back to the talking about the SC100, it's 2 instruments in one also. It's the dynamic light scattering as well as zeta-potential. Now, I'll let you go to the HORIBA application notes and read up on zeta-potential if you're interested. Here, the image is showing a negatively charged particle, and then here we have the double charge layer around a particle. At the shear plane, the zeta-potential is defined. So zeta-potential indicates dispersion stability. This is very important if we're talking about coagulation, flocculation. These types of measurements are done in the lab to help optimize coagulant and polymer doses. You see here the green line represents a zeta-potential of 0. Again, this is measured on using electrophoretic mobility. The 0 is the isoelectric point, and it will give you results on whether, and in this case, the result is it's negative, or it could be positive. And then also we want to point out that we also have an automatic titrator with the SZ100, so that, you know, this is just a particular sample at a particular pH. But if you are interested in zeta potential as a function of pH, you can use the automatic titrator with this instrument and get that type of information. And of course, you know, I keep saying we, you know, it's Danny and Tyra and Stephen and Ali and Jill and Dale that keep the lab going and do all this, you know, the real labor and work. I just analyze data in awe of what we can do with our suite of instruments and learning about organic matter in water. I have a couple of pages here of references, and again here, and I'll end up with our email addresses again, that you certainly should feel free to contact us, or if you need any of these references, or if we can further discuss. You know, I love talking about this. It's my favorite topic, so I could go on and on, but I'm sure Julie is getting nervous and wants me to finish and be quiet. So Julie, I'll turn it over to you.
Thank you so much, Martha. Thank you so much for the excellent talk, and thank you, Katie. It's actually perfect timing. I am not nervous at all. We do have questions that came in, and I think now would be a good time to tackle them. Are you ready?
Sure.
All right, so one of the questions that came in is, bacteria need particles to grow on. What are the particles, and how can we use this technology to reduce drinking water CFU?
I can jump in on this one a little bit. Bacteria can be free floating as well as attached to particles. So want to make sure that we're clear that both of those things actually occur. And actually, one of the things that we're looking into right now is an innovative online bacteria probe using fluorescence. We're trying to use fluorescence to actually look at the tryptophan signal, which is indicative of bacteria. And so there are a couple of probes that have been introduced into the market. And so we're actually digging into a little bit greater detail to make sure that we can validate with the HORIBA Aqualog what we're seeing claims made by this probe manufacturer for. So it is something that has some great potential in terms of monitoring bacteria. The challenge is the detection limit and the concentration at which the tryptophan is present in the water samples. So that's one potential application.
Oh, yes, here we go. So this one is not a question, but someone commented that Martha has 3 email addresses.
I only shared 3.
All right, this question, this person asked, is there an issue with Teflon filters, or why does it have to be a PES membrane?
Yes, you want to go with the PES membrane. Now, there is an article, I don't think I added this to this reference list, but you can email me at any of those addresses and I could provide that for you. But there was a study done a few years ago by Dr. Karen Phil at, I believe he's still at Clemson, and he did a study of what filters should be used. And you really do need to use a membrane filter. You need to use that PES filter. And again, it's in the literature, and that article would point that out. And we use that filter for all the suite of instruments. One thing I forgot to mention is, we filter for, we get DOC, and then actually the cuvette from the aqualog can go directly into the SC100 instrument. Now you may want to, you've got to decide whether you're going to use sodium azide. You may want to add it in between there. And again, we don't practice adding sodium azide for the EAMS. But yes, you want to use that filter. It has been shown again and worked by others that it has been shown to be the filter that will absorb the least amount of the sample that you want to put through there. And absolutely you want to avoid cellulose filters.
Thank you, Martha. Next question. What chlorine quenching agents and preservatives would not affect EEMs? And what's your suggestion?
Well, we have done something recently with sodium sulfite, and Katie, you can jump in here too if you want to. And if you're concerned, you need to run, spike a blank and run it to test it. So yes, we do. That is a concern about quenching the chlorination before you go to the EAMS. But again, my suggestion always is to run a spiked sample and see if you have any concerns.
Thank you. How does this process work, and what are some practical applications? How cost effective is it?
Martha, do you want me to hop in on a couple of examples?
I'm not sure if they're talking about the analytical process or in the lab. Take it away, Katie.
Yeah, I'm going to presume that it's kind of a broad question around how do we use these instruments for optimization of treatment processes. And there's a number of different ways we can do this. Martha's talked a lot about molecular reagglomeration. That's something that we know is a causative mechanism for RO membrane fouling. So that's been one of the things that we've been looking at using these tools. Another potential application is the optimization of coagulation, flocculation processes. And when we start digging into either drinking water treatment or even looking at these techniques for optimization of biosolids dewatering, that's also a good application. We can see cost savings on the order of 15 to 30%, depending on how far off you were. Those are real dollars when you start talking about the annual operating costs of chemicals for those given treatment processes. So there's a couple of examples of how we can leverage these techniques within treatment processes for optimization.
Thank you, Katie. Next question, what filters would you recommend instead of the cellulose filters?
Okay, we recommend that polyether sulfone filter, the PES filter.
Okay, the PES filter.
And many different manufacturers, you can get that from several different vendors, but that's the makeup of the membrane filter, and that's what we recommend. And we're using it on everything related to organic carbon in the laboratory.
Thank you. This question is a little bit more general, so either of you can jump in if you like. Can you comment on the levels of reduction at different stages of advanced wastewater treatment?
Katie, you want to take that?
Well, that's
we have a new publication coming in.
We do have a publication that we're working on right now, specifically around ozone biofiltration, both as applied as advanced wastewater treatment process, as well as in drinking water treatment processes. And what's interesting is, not all, and Martha, I don't remember if you said not all organic matter fluoresces. So we're
Thank
really only looking at a small fraction with fluorescence. So particle size can actually also be a meaningful and helpful tool in this. But yes, we can use this tool to inform how certain fractions of organic carbon are removed throughout various treatment processes. And it also gives us some insight into particular changes or transformations. One of the things that I think is really exciting is the work that's going on with ozone biofiltration right now. We can actually see the carbon characteristics changing through the fluorescence, as well as how those molecules will aggregate before and after treatment. So those are a couple of examples. I think the question was, can you tell the percentage of removal? No, you can't tell the percentage of TOC removal, but you can look at the percentage of removal of certain fractions of those organic carbon macromolecules. Martha, anything to add?
I think that's good, and thank you. I got through this without saying the important thing: not all organic matter fluoresces, and you must never forget that. Thank you, Kate.
What is your bulk estimate of how many treatment plants are routinely implementing these techniques, FEEM, particle size, and so in the water quality labs?
So we actually see particle size distribution analysis being applied in wastewater treatment, particularly around monitoring filtration processes or even for disinfection. And so I would say that overall on the wastewater side, it's probably a very small percentage, maybe 3 to 4, maybe 5%. On the drinking water side, I think we see a little bit more uptake of these technologies, typically because I think we're used to applying similar techniques in drinking water already with UVA. And so this is not a huge leap into looking at those sorts of tools as an assessment method. I would just gander a guess that we're still under 10% of uptake within drinking water treatment facilities. And, some of it is around the cost of this equipment and the training and the capacity building that needs to be done in terms of operator training. And so I think what's interesting is when you look at the cost of these instruments in context of the ability to optimize treatment cost as well as improve treatment compliance with regulations, it's actually quite a small cost. And particularly when you look at other analyzers that we use within the water quality laboratory at drinking water and wastewater plants, I think it is something that has huge potential to have a greater uptake in the market.
Absolutely. Thank you, Katie. Now this question, and I think we have time for one more question. This person wants to know if the nanopartica, so the SZ100 dynamic light scattering particle size analyzer, can it be used to track nanoplastics, which should fluoresce?
Yes, I do believe it can, and in fact, for the SZ100, you're using polystyrene latex particles as standards, and those are nanoplastics. And it does not, for the SZ100, it does not have to fluoresce to be detectable. So yes, I think it can be used, and when you use, and HORIBA recommends using, polystyrene latex standards, that when you use those standards, you are measuring a nanoplastic particle.
And I'll add that. Go ahead,
I was
Katie.
just going to add, Julie, that HORIBA has a whole other suite of other analytical instrumentation around Raman spectroscopy that is being investigated for micro and nanoplastics. And it's on my wish list of things to buy. And we're hoping that Julie's going to give us a discount for helping her with the webinar.
Sure, why not? I get to say whatever I want. Well, I think this is a topic that everybody holds very dear to heart. I would say that PSL, we chose that because it's NIST certified. So it came with a certificate as opposed to those nanoplastics that you might be drinking from bottled water. But to explore more, you can certainly email us at labinfo@horiba.com, since I'm sure there's a lot more to it than just tracking the nanoplastic size. So I think I have used up all your time. I want to thank you, Katie and Martha, so much for preparing this and for the excellent talk. For those of you who have attended, thank you so much as well. Don't hesitate to reach out to us, again, at labinfo@horiba.com for any questions and feedback. Please take a minute of your time also at the end of this webinar to vote to our survey. I would appreciate it. It will help me understand how to better our next webinar. Our next webinar is going to be on June 8th, where we're going to switch topic from water treatment to nanoparticles in CMP. Is there anything else that you would like to add before we wrap up, Katie and Martha?
Thank you, Julie, for the opportunity.
Thank you as well. All right, bye for now. Thank you so much.